So physics experiment and detector summary. You were all here on Monday, but still I will say a few words about the vision and strategy. What is it? On the vision and strategy that was discussed this day. And then on Tuesday and Wednesday, we discussed the implementation of the strategy. And I will take this opportunity to tell you what can be your contribution. We're looking for people to work with us and to achieve the goal of the feasibility study. So I will address the software, the detectors, luminosity, and center of mass energy measurements, and put some highlight of the physics studies. And finally, on Wednesday, we had a roundtable about convincing the world of the vision and the strategy that we chose, with the first question that was, is the FCC physics case sharp enough? And this was here, and I will discuss that too. So the scientific vision is normally well known by now. After the Higgs boson discovery at the LHC, and the fact that it didn't find any BSM physics, the results have forced us to think differently about BSM physics. And the days of guaranteed discoveries are now over, but the big theoretical questions remain wide open. What is the hierarchy problem, the origin of flavor, the origin of neutrinos, the dark matter, the baryon asymmetry of the universe, etc. Having no theory guidance, this implies that the future high energy physics progress is to be driven by experimental exploration rather than by theory biases. As a consequence, and Christophe told us that, we need a broad, versatile, and ambitious program that sharpens our knowledge of already discovered physics, for example, the Higgs, which we just discovered, and pushes the frontier of the unknown in the intensity and energy frontier. The FCC does exactly that, and it brings us more precision, more energy, for more sensitivity to new physics. New physics, be light and too feebly interacting, or too heavy, or leading to too soft final state to have been discovered at the LHC. We need a more powerful machine there to do that. Now the strategy, the European strategy, does not say otherwise. It says exactly the same thing, actually, with its own words. It says we want a Higgs factory, electron-positron Higgs factory first, and we want the proton-proton collider at the highest energy achievable next. And then they told us, please do the feasibility study of the FCC. The program of the feasibility study is even funded by the CERN Council, and it will cover the integrated program, FCCIS and FCCHH. The reason why we need EE and PP collider actually is provided by the Higgs already. And let me walk you through that in a minute. The FCCIS measures the production cross-section of ZH. And this production cross-section allows you to determine the Higgs ZZ coupling to 0.2%. It's an absolute measurement, model independent. It's a standard candle. It fixes everything else. So it's here in the table. Then the FCCIS continues with the most copious decays of the Higgs, with 1 million Higgs that it has, and allows to determine in a model independent manner, thanks to the standard candle, the WW coupling, BB coupling, CC coupling, GG coupling, tau tau coupling. All this is EE. It doesn't do the rare decays. The rare decays will be done by the FCCHH, which produces over 10 to the 10 Higgs boson. And the standard candle of the FCCIS will in turn fix these couplings here to a very good precision as well, 0.5%, something like that. The FCCHH also produces 10 to the 8 TTH and 2 10 to the 7 double H Higgs pairs, which in turn allow to access the Yukawa coupling of the Higgs to the top and the self-coupling of the Higgs. But it still needs the FCCIS to have a good precision on these numbers. Indeed, the FCCHH measures the ratio of the TTH or TTZ cross-section. To have the TTH, you need the TTZ, and the TTZ is done by FCCIS. And you see what it will be the precision of the Yukawa coupling here, the top Yukawa coupling, without FCCIS, this is the dashed line, and with FCCIS. And in turn, the self-coupling of the Higgs would be determined much less well if the TTH coupling would not be determined thanks to the FCCIS. So as a consequence, the FCC, or as a conclusion, the complementarity between these two machines is just outstanding, and allows to reach precision that is unreachable by high-energy electron colliders. Sorry to have been long there, but I think it was essential to recall that. Now, FCCE is much more than a Higgs factory. It also includes the top at larger energy and the intensity frontier at lower energy, making the FCC a Higgs, a top, an electroweak, a bottom, a tau, a flavor factory of sorts, and also allows for direct searches for light new physics, which leads to very rare decays. So there is an amazingly rich field of studies with exploration opportunities unique to FCCE, which in turn imposes a whole new level, a whole new level of requirements to detectors, to the theory calculations, and to the collider operation. The heavy physics reach is just astonishing. And indirectly with FCCE, whatever direction, each line here is a direction, whatever direction you look, you have a sensitivity of several tenths of TeV due to the precision of the measurements and to the completeness of the measurements. And the same for FCCHH. Directly, whatever direction you look, you may find a new particle. Now, whether you find something or you see a deviation or not is irrelevant. Of course, you are all happy when you discover a peak in a distribution. But even if you don't, the precision expected with the FCC multidimensional approach, all direction, will allow a multitude of new physics models to be rejected, thus strongly limiting the field of possible new physics interpretations, and will provide a clearer vision of what to look for, either at the high energy scale or beyond, or for light particles with much weaker coupling. So this led Tevong in the parallel session, to call the FCC a general purpose particle observatory to explore the BSM origins of the laws of our universe in a wide-ranging physics program. So rather than yet another expected search for supersymmetry, the FCC should be seen as an origins explorer and possibly an origins identifier. It may be able to identify the origin of matter, of the Higgs, of flavor, of dark matter, of neutrinos, and even the origins of the standard model. Even if when you do measurement of the standard model particle properties, you do BSM physics because the standard model is known to be an effective field theory of an underlying ultraviolet theory that it originates from. So there is no SM collider. All colliders, even when you do standard model measurements, is a BSM collider. Now, timescales were presented by Michael on the first day, and the timescales defined by Michael actually define also the highest priority goal of for PED during the feasibility study. We'll have to have proto collaboration just before the approval, detector TDR in 2030, start detector construction a few years later, and start detector installation at the beginning of the 40s to start the detector commissioning when the first collision arrive. So the focus, obviously, is to set the scene for the FCC-EE proto collaboration. We need to sharpen the physics case. Have we discovered everything that the FCC can discover? So identify open question, observable BSM model, etc. We have to match the experimental and theoretical uncertainties to the statistical precision, which is fantastic. So there is a lot of work here. This is done by doing complete case studies of benchmark physics processes, development of state-of-the-art physics tools, detector requirements and plans for theoretical calculation, and measurement of the center of mass energy. You see that the program is very ambitious here. And then you have to benchmark several detector concepts to demonstrably match the requirements that you have produced in the case studies. And this will provide guidance to coherent R&D efforts, of course. To do all that, you have to develop the common infrastructure of the software, and you have to build the community. Of course, the priority is in the other way around. You first have to build your community, and then finally sharpen your physics case. This is a lot to do in a few years. The challenges arise from the richness of the physics program, and we have to try to do all that. Excuse me, I am not going in the right direction. First, build the community. We have a new management team for about 6 months now, which is at work towards reaching the highest priority goal. You have the names here. The links with the ECFA working groups is essential and timely because they allow fruitful collaboration and communication with the linear collider community, which have the experience. And the mission of this management team is to pass the baton to the younger generation and start a knowledge transfer. And it was really a pleasure to see young faces presenting talks in the parallel sessions. Software. this is the first thing to do, because this is the underlying tissue that connects the physics studies, the detector concepts, and the detector R&D. We try to exploit all possible synergies in the community to make that possible in the few years that we have. The software framework will be common to all FCC experiments. This never happened until now. Each experiment has had its own software. And the software framework and content is developed in a common effort with LHC experiment contribution. FCC will be compatible with FCCIE and EH and has huge contribution from ILC teams, CLIC teams, CPC, EIC, and ECFA. We can already see the benefits of this collaborative approach. They are visible. We have already a framework, T4HEP, a data model, EDM4HEP, and a geometry, DD4HEP, common to everybody. The ongoing priorities are where you can contribute. You actually can contribute in many places for the software, but let me highlight a few here. The plug and play technology to be able to use that subdetector with this subdetector for the tracking and the calorimetry to optimize your detector concept simulation. The use and optimization of reconstruction tools developed in linear collider studies, the feedback on the analysis framework. When you do analysis, you can do feedback, and you have to develop a visualization tool. A new structure is being put in place to address the challenges and build a community. And of course, this is such a cornerstone to the whole effort that the support from the FCC community is needed, both from the users and from the bosses, to maintain a small CERN core group to lead the effort. There was an important development about detectors, again given by Michael during his talk the first day. He presented the new layout of the ring with fourfold superperiodicity, which is compatible with 2 or 4 experiments. Before it was compatible with only 2. And FCCIE would greatly benefit from having 4 interaction points. It's more data sooner, even if I heard that now we should use 4 IP to compensate for the smaller luminosity. I will fight against that. It will bring redundancy and in turn systematic robustness. Just remember the MZ measurement at LEP, which would not have been correct with only 2 experiments. And better physics coverage with different detector technologies and abilities. It also offering 4 interaction regions is also of great interest to cover all detector requirements. We have a number of requirements which may be conflicting. Some coming from the ultra-precise electroweak and QCD program. Some coming from the heavy flavor program. Some coming from the detection of feebly coupled particles. Some coming from the Higgs factory. They are not all compatible. So having 4 interaction allows to have 4 different detectors with comprehensive sets of detector requirements. Note that you should not read all these requirements because they are linear collider inspired and should be updated from physics studies at FCCIE with the much larger luminosity and the much larger physics case that we have. So to give you an example of possible conflicts, in calorimetry, you cannot have, or maybe you can, but it has to be checked. You cannot have high electromagnetic precision, high granularity, high stability, small cost, particle ID all together. So you have to make compromises. Tracking, transparency versus segmentation, momentum resolution, time resolution, power consumption, all this may lead to conflicting decisions. So all in all, it calls for at least 4 detector concepts to be benchmarked during the feasibility study. This will be tough, which in turn will provide guidelines to the R&D efforts. The detector R&D, there were 2 presentations by Auguste and Nicolas showing how the detector requirement may guide the silicon tracking vertexing on the one hand and the high granularity liquid argon calorimetry on the other. Here is an highlight. There is a lot of synergy on silicon tracking with other R&D projects. And we saw that there were important similarities between the FCCIE requirements and the EV ions experiment, like the ITS3 in Alice. One good example is the bend sensors for the Alice ATS3 design, where you can really bend the sensor and put them around the beam pipe for a better flavor tagging precision. The development in high granularity liquid argon calorimetry allow now to reach 10 times the Atlas granularity. This is done by inclined readout absorber planes with respect to the direction of the incoming particles, and several longitudinal compartments for the readouts, and some nice possible geometry for the end caps, which would do about the same. The FCCIE requirements also inspired an innovative R&D, Granita, by Jacques Lefrançois, with several ideas there, which may be really going a great deal for detectors, using small crystal grains of tungstate of zinc, which is very easy, he said, similar as growing salt grains with the water and the sun. It brings to excellent energy resolution like monocrystals, but it's also much less expensive than monocrystals because of the easy growing. And then the scintillation light is collected with optical fibers. This is the first idea. You see here the grain salts and the salt of this crystal. Then we use the fast and slow scintillation light components for PID in the pulse shape in the fibers. By doing the difference between the slow and the fast, you see that you can, this is called the PSD parameter, you can identify the various particles. The hope is that this built-in particle ID may be used to determine the electron over hadron ratio, as is done for scintillation and Cherenkov flight in dual readout calorimetry. And this is very attractive to put this in front of a dual readout HCAL, for example. Jacques then proposed to use simulation of the pulse shape to evaluate the precision of the method, but Franco Bedeschi said that maybe we have already data with former data, with former testing campaigns with the PGO, so we'll see that. Very quick overview of possible detector concepts as we use them now. They are bound to evolve because they might or might not be adapted to the FCC detector requirements. Simulation studies will tell us more. Detector R&D may improve them. Again, there is here plenty of room for individual contribution. We have CLD, which is a well-established design from the linear collider community and adapted for FCCIE. Well, there's still some adaptation to be done on the electronics and the cooling to account for the fact that the repetition rate at linear collider is 50 Hertz, and we are 40 megahertz, so we need more cooling, different electronics, etc. It is all ported in the software of FCC. Another design that was in the CDR as well and presented by Paolo Giacomelli include a ultralight drift chamber with helium, so quasi-transparent, and a dual readout calorimeter. And they are thinking of putting crystals in front of the dual readout calorimeter in order to have a good electromagnetic resolution, still having the dual readout advantages, and longitudinal segmentation to make the identification between the photon and hadron. This is expensive, so maybe here even a calorimeter with Granita would be unvisionable. Software is under active development and being ported to the CCSW. And there was a third detector concept presented for the first time at this FCC week, based on noble liquid ECAL, so the thing that I just presented here, and with other subdetectors for the tracking and for the calorimeters. The full simulation of the ECAL is available in FCCSW. And the good thing now is that you can plug and play in the software, because it's all done for that. You can put the tracker you want, like the drift chamber of IDEA. You can put the iron cylinder high granularity HCAL if you wish, and see with the simulation what is best for FCCE. You can use also the tools that have been developed in FCCE, clustering, particle flow, you name it. And this is how the things will progress. You develop something and you reuse it from something else. A considerable detector challenge for all detectors is, and of course, an opportunity to contribute decisively is given by the luminosity measurement with low angle Baba scattering, E plus E minus to E plus E minus. We have a very ambitious goal for the absolute normalization of this luminosity, 10 to the minus 4, much better than at LEP. And the LumiCal, which is represented here, is also in a much more complicated position because of the very much penetrating MDI. You have only 1 meter here to put your detectors. The detector geometry is to be controlled to 1 micron. The distance between 2 monitors to be controlled to 100 micron. And the CDR LumiCal design is squeezed from 2 sides. You have to stay away from the beam pipe and stay inside 150 milliradian zone. So it's extremely difficult, but we have to do it. We cannot do otherwise. Now there could be, to deal with that, an FCC contribution to the FCAL R&D collaboration. This was presented by Wolfgang, who designed the Lumical for ILC and CLIC. But as he told us, their activity would benefit from a boost, and we need them, so we should work there. There is an alternative case study to be made, which is to measure the luminosity with diphoton at large angle, which is theoretically in statistical precision of 2 × 10⁻⁵, with the question mark of the background, huge background at large angle from E ± to E ±. So maybe it's not feasible, but it is a possible contribution for you. This has already been summarized by Jacqueline in the first talk. Square root of S measurement, with resonant depolarization. Resonant depolarization is the cornerstone of the precision program of the CCEE, because all the electroweak observables depend on the center of mass energy a great deal. So you really need to measure it with a great precision. And this group is here for that, to demonstrate a feasible program of measurements and procedures to allow a determination of the center of mass energy and spread. For physicists, particle physicists, you can do measurements with physics events. For example, E ± to mu ± gamma. There was a number of things done in the CDR, but not much since the CDR. There is a lot to do here and to learn. So take that if you are interested. Note that the resonant depolarization is also a cornerstone of the precision program well beyond the FCCE. There was a recent CDF measurement of the W mass, which is remarkable in 2 ways, as Alain put it. First, it relies on the precise calibration on J psi, epsilon, and Z masses, which are all measured in circular E ± collider using resonant depolarization. So the W mass of CDF uses resonant depolarization at E ± collider. And also Alain remarked that they manage, after a lot of work, to reduce the systematic errors to the level of the statistical precision, which is actually the trade-off of the precision physics at FCCEE, and this was useful to remark. Speaking of physics, the team of physics group young conveners has now been assembled. The last one 2 months ago, I think. Excuse me. All these young conveners, which you see surrounded in red, and we added Janusz and Philip for presentation on the precision and on the top. They presented the program of the group and a list of opportunities for contribution. I could not manage to summarize that because it's not really summary talk material. It's a list of contribution. So I suggest that you look at the slides to pick up your contribution, the one you like best, and even propose new ones. So let me do a little bit of publicity here. It's not just an advertising slide. I'm speaking from experience, my own experience. Your choice will be good, whatever contribution you choose. The work you'll do will be both interesting and rewarding. It will be guided by physics first principle. So you'll use your brain, Feynman graph, matrix elements, symmetries. It will be entirely new, though at times guided by past experience and CDR estimates. Indeed, who worked with 10⁻¹² Zs before? By the way, how do we do that? It's all creativity. You'll carry out a physics study from the beginning to the end. You'll have to find original solution to reduce sensitivity to uncertainties, which will be huge at the beginning. And it's only your cleverness which will allow you to reduce them, both experimentally and theoretically. For example, by making ancillary measurements, independent measurements, inventing new variables, you name it. You'll reduce accordingly the demands on detectors and on theory with clever tricks. And you'll be thanked for that. And you'll contribute without even noticing, because it will be part of your work, to the development of physics tools, which in turn will benefit others through the common software framework. And finally, last but not least, you'll come up with a publication of your work with your sole name on it, which is rare in particle physics these days, or maybe with that of a few colleagues in your team. Now for the physics project, how much time do I have? 5 minutes, so maybe I need 8. The work is starting now. So I will just present a few highlights, focusing on what is new. So don't expect much. The work is starting now with fresh physicists, fresh and young, with brand new and evolving software, with an important load of knowledge to be transferred from the old guys to the young guys, and with a speed proportional maybe to the square of the number of new people involved. So do not expect feasibility study report material here, not even midterm review material yet. It's just to let you know what is going on. The most important message is that the new generation start committing to the work and start owning the FCC project. And I think it is very good news. It should go faster. They should be more numerous, but we see the trend. So we had a number of presentations. Maybe I take 6 examples. Higher order calculation of electroweak precision observable. Janusz presented the first full 2-loop calculation of the Z total width in the standard model, arriving after years of calculation to a precision of 500 keV. Excellent. Now, if you look at the experimental precision that we have now, that we project, it's 25 keV. So there is still an order of magnitude to gain here. This will require 3 or 4 loop calculations to meet this uncertainty. And this uncertainty may still decrease. So you see that the work to do is not small. Flavors, there is a fantastic opportunities there for flavors, even after LHCb and BEL2 program. The FCCIS combines the advantage of LHCb and BEL2. You see the advantage of LHCb here, the LHCb of BEL2 there, and FCCIS has almost all of them, with 10 times larger statistics than BEL2. Maybe the very rare decays that will have been discovered at BEL2 will make CP violation studies possible at FCCIS. You see here the ratio of statistics. The first plot that was made allowed to show the much higher height and better separation for BD and BS to mu plus mu minus using the exquisite tracking from the idea drift chamber. For comparison, here is the same plot, here in the same window here, for the LHCb separation. You see, of course, a complete case study is required with the background, with the systematic uncertainty that you have not thought of. But this is an interesting perspective. Speaking of complete studies, they may bring bad surprises. We had the full revisit of the flagship channels, B to K star tau tau, which is a flagship channel for lepton universality studies, towards detector requirements. The CDR predicted 1,000 events and very little background. This is the peak of the interesting events. And this is the final state that you're looking for with a primary vertex, a secondary vertex, and 2 tertiary vertices. Now they try to include all the backgrounds, even the background that they thought would not contribute. At first, they reduced the estimate of the signal events, but they have also a overwhelming background. You see the scale here; it's 100 times larger. You don't see the signal. Signal should be here. You don't see it. The dominant background come from this decay with a GS decay, which is very exotic, pi 0, and an unexpected kinematic conspiracy, which put it in the wrong way, in the wrong place. Don't be too worried. The work is going on. The work is in progress to find a solution to reject this and other backgrounds. So stay tuned. You may come back to this, but this will require work. Top group, there was an optimization of the top pair threshold scan. In the CDR, the baseline scenario was to do a scan with 10 points. And it was realized that we didn't need 10 points if we were to measure only the mass and width, given that FCCIS measures alpha S and the top Yukawa coupling, or FCC, independently in separate ways. So 4 points would be enough and would allow to bring 25% better statistical precision on the top mass compared to the 10 equidistant measurements. The FCCIS measurements are here before with 10 points and now with only 4 points. Physics tools, there was a fantastic presentation on the flavor tagging algorithm using all possible input features that a detector with particle ID would give. Detector with 3 pixel layers and with cluster counting and time of flight with 30 picosecond resolution. Using all the variables, kinematic variables, displacement variables, the identification variables, you can reach a performance not only for B and C tagging, but also for S tagging and gluon tagging. So I don't ask you to understand this curve right now, but if you look at the point around 65% efficiency for the S tagging, and you request to detect 2 S jets, you reach an efficiency for this SS bar decay of the Z, for example, of 40% for only 1% of the other events. So this allows for several additional electronic measurements in the strange sector. This was never done at LEP and SLC. You can reach the same efficiency for gluon tagging and even a better background rejection for the Higgs, which allow for gluon fragmentation studies with a pure Higgs into gluon sample. We will have 100,000 such events at FCCEE, for example, with the tag and probe selection, and therefore understand the differences between the various generators in these decays. The direct search for feebly interacting large particles restarted again to fully exploit the intensity frontier to look for heavy neutral leptons, action-like particles, and its boson with exotic decays. An example is given here for heavy neutral leptons. 1 minute, I will have 3 slides on the discussion at the end, so this is fast. Realistic case studies in FCCW with background are started to possibly design large or not large detectors with long-lived particle in mind. And also an analysis, if the heavy neutral lepton signal is detected in the now celebrated curve, sensitivity curve for FCCEE, they are starting to design optimal variable to disentangle direct from Majorana heavy neutral leptons using the angular distributions and the polarization distribution different for both kind of neutrinos. More to come soon. The distribution that were shown were not really a presentation material for the summary talk, but stay tuned, it will come soon. Last topic, 3 slides. Convincing the community, convincing the world. Well, looking at what you just saw and the rest in the FCC week, the physics prospect of FCC appear to me to be vast. They seem to be addressing some of the most important questions in nature, exploiting maximally the complementarities and synergies for both the intensity and energy frontier. But this view is not yet shared by all. For example, the CERN research director told us, during the physics workshop in February, I strongly believe that we have to strengthen and sharpen our physics argument. Just higher precision is not enough. Sharpen the physics case for FCC, etc. Now, there are possible hints of an explanation that were given in the talk of Meenakshi in the SNOMAS presentation on Monday. This plot was shown, which I thought was outrageous, but it was also made by fans of muon colliders, so we may misunderstand. So what does this plot show? Physics potential, R&D attractiveness. It shows that the FCC physics potential is not well appreciated or understood by everybody. It shows that the FCC R&D is not felt attractive. Strange. It shows that the FCCEE and FCCHH are not part of a single project. They are shown separately, while it is the integrated project that makes the difference. In this SNOMAS talk, also, FCCHH clique and muon colliders were called BSN colliders. That was the first time that I heard that. The FCCEE, consequently, would be viewed as an SN colliders. So it means that in the common understanding, for those people who have not tried to think deeply, the precision frontier sensitivity and the sensitivity to feebly interacting particles are not on par with energy frontier. So we need to work on that to change this view. So for this, a roundtable was organized on Wednesday by Matthew Chalmers with this topic: is the FCC physics case sharp enough? The panelists were Rebecca for FCC and Bruno, Oliver, and Patrice, not proponents of FCC, rather proponents of muon collider, all proponents of ILC, proponents of gravitational waves or quantum material, you name it. So first, Rebecca summarized the FCC physics case in a creative and effective manner. I suggest that you go to her site, they are very poetic. And then the panelists were asked to give and explain their opinion about the physics case. One slide after this one. And the answer was straight. I think the FCC physics case is very strong and very sharp. The FCC physics case is compelling. I am fully supportive. The FCC scientific case is great. We are lucky to be able to think of such a project. So these are very strong and positive statements, but the FCC physics case seems to need, and therefore the FCC physics case seems to need no specific sharpening. And the rest of the discussion changed. It was not the answer to the initial question. It went on to understand what is not convincing about the FCC at large, which in turn will help us to tune our communication. So here I have a number of statements that were made, maybe not all of them are here. Young physicists are not excited about the repeat of LEP and LHC. the flow of the project, a deadline in 2045, then one in 2070, and that's it. The timescales are such that it is not of use to maintain a community for so long. Maintain other collider projects, be it at R&D level. Diversity is important. Recruiting the best students have become much harder. It's on us, all that. We need to communicate to show that it is interesting. Competition with new development in fundamental physics may give faster return, and gravitational waves and quantum technology was cited. Compare expected scientific outcomes and timescale with other projects in the discipline. Put FCC in the bigger picture. How are we going to avoid the SSC fate? Important for young physicists to take ownership of the project, to engage with interesting and rewarded work. And there was a plea, please change the name. Future sounds like it will not happen. It is happening. And circular automatically recalls linear. So we need to make the name concrete and unescapable. And maybe we should launch a competition today to have the best name for FCC. Final slide. A number of suggestions were already made to improve the convincing. We should think of what was said and come with a message that addresses all concern. A paper like FCC, your questions answer or your concern answer is already taken, but we can happily give the copyright. We should not be shy in emphasizing the immense breadth and richness of the program. We have a very lively and diverse program for FCCEE, which changes almost every year. It's not that we have one deadline. Tremendous high energy prospect for FCCHH, challenging R&D for FCCE and FCCHH detectors in order to approach the frontier. More scientific than one can imagine, with likely 10 to the 4 publications or more, starting now with the case studies, and program conducted by at least 10, maybe 20 separate experiments addressing the full range of HEP. And certainly, we should be putting more effort in spreading the word within the community and outside. And I stop here. Sorry for the delay.
Thank you.